In this video, we're going to talk about slope fields. Alright, so recall we have this differential equation dy dx equals y prime. Alright, the derivative is just the slope of the tangent line to our original function. Alright, and we can say a slope can be positive, negative, 0, and 5. So if it's positive, we know our line's kind of going upward in that direction. If it's negative, it's going down that direction. 0, it's going to be perfectly flat. And undefined, a few different things can happen. There could just not be a tangent line, or it could be going straight up and down. That doesn't have a slope because the y values, or sorry, the x values are the same. Alright, so consider this differential equation. Dy dx equals 3x plus 2y minus 4. For every single x and y, we could figure out what would the slope be of a point there. So for instance, I could plug in 1, 1. And the derivative, the slope of the tangent line, is going to be 3 times 1 plus 2 times 1 minus 4. And I get 1. So if 1, 1 is on my graph, the tangent line would have to have slope 1. All right, so that's going to kind of help me figure out what the shape of my original function is by just kind of thinking about what all these tangent lines and what shape they're going to have. So I can do this for every single point and kind of figure out what the tangent line would look like. So at 1, 1, this tangent line would have slope 1, which is just a line that looks like that, like a kind of perfect diagonal line. All right, so when I put all these points together, I'm going to get something that looks like this. All right, this is a slope field that represents this differential equation. So for every single point, I think these gaps are a half. So 1, 1 would be right here. You can see that perfectly diagonal little line that has slope 1. All right, so you go through and you plug in every single value, and you create a little line. And these slope fields kind of show you what direction your graph should be following. All right, so if I have a solution to this differential equation, it would kind of follow these lines. All right, one thing you might have to do for the AP exam is create your own slope fields. All right, so here we have all these different points. Basically, just plug in the points and draw a little tiny line at that point. All right, some things that students always worry about, like what if my line's not perfect? All right, there's some things you should definitely have perfect. First of all, if your slope is positive, your line has to be going upward to the right. If your slope is negative, your line has to be going down. All right, so those are non-negotiables. If your slope is 1, it should be that kind of exactly kind of 45 diagonal line. If your slope is greater than 1, it should be steeper than this, so it shouldn't look like the diagonal, it should be steeper than diagonal, so I can be able to tell that's steeper than 1. And my slope is less than 1. If your slope is less than 1, then it should be less steep than that perfect diagonal. So if I had the perfect diagonal, it should be less steep than that. So that's really all you need to know. If it's 1/3 or 1/2, it doesn't have to be exactly that slope, but you should definitely be able to tell it's less than 1. All right, so let's just do a few of them. All right, let's plug out the point negative 2, 2. All right, I'm going to plug that in. My slope there is negative x over normal y. And this one I get exactly 1. So at this point, negative 2, 2, my graph should be that exact diagonal line 1. So I'm just going to draw a little line there. All right, negative 1, 1 will also cancel out. Let's try another one. Let's try, let's go over here, 1, 1. So try the point 1, 1. dy dx is going to be negative 1 over 1, which is negative 1. So at 1, 1, the slope is negative 1. So now it's going to be that perfect diagonal line, but it's going down to the right. All right, and that would be the same, 2 over 2. Let's try one where they're not the same value. So we can try like, let's try, this one's good. Negative 1, 2. All right, so dy dx there. Negative 1 over 2 is 1/2. All right, so it's positive 1/2. All right, if this is my perfect diagonal line at 1, it needs to be slightly less steep than that. So I can compare these two. All right, this is my 1. This one's definitely smaller than 1 because it's less steep. And then I can do the same for negative 2, 1, dy dx. Negative 2 over 1, and that one's 2. So at this point, negative 2, 1, my slope is 2, so it should be steeper. So again, if I think about the perfect diagonal line, it should be steeper than that. And I could be able to tell that it's going up faster. All right, so I could just keep going through this. Get a little tedious. 1, 2 is going to be -1, -1/2. Here we're going to get -2, so it's steeper. Oops. -1, -1 is going to be negative. This is also going to be -1, 2/1, -2, -1/2. This is 1, -2, so it's going to be +1/2. These are going to be +1s. This is +2. All right, so you can kind of see this almost like creating like a circular shape. So it turns out the solution difference equation here are going to generally look like circles. I haven't done anything on the axes yet. If x is 0, all right, we're going to get 0. So these are all going to be flat. And if y is 0, we can't divide by 0. We'd get like infinite values, so you can make these vertical. All right, sometimes you just don't put them at all. Sometimes you put them vertical. Normally in the AP test, they kind of ignore when you get these undefined ones. But I would put them as vertical lines because as you get closer and closer, they just get closer and closer to vertical. All right, so you can kind of see these circular shapes happening for this one. All right, and the only thing that changes if we have different thing is just you're plugging into a different thing. So I'll just do some of these real quick. If I did 2, 2, dy dx is 2 minus 2, which is 0. So at 2, 2, I have a slope of 0. What about at like, I don't know, -1, -2? dy dx is my y value, -2 minus my x value, -1. I get -1. So at -1, -2, I get -1. And I can just keep doing this and getting all these different slopes. Again, the important thing is if it's 1 or -1, it should be the exact kind of diagonals. Smaller than 1, they should be less steep. Bigger than 1, they should be more steep. And 0, they should be exactly flat. All right, so go ahead and try this one on your own. All right, you're doing it for x times y. All right, so I'll pause the video, try it on your own, and then when you come back, there will be all the lines put on. So I'll show you the answer in 3, 2, 1. And here's something like what the solution should look like. So pretty much when either one of them is 0, the whole thing's 0. So you get all these kind of flat, horizontal tangent lines on the axes. And then you get 1s, some 2s. So 2s are steeper than 1s. And then some 4s. 4s are steeper than 2s. All right, so you can kind of see as I go out away from the origin, these lines just get steeper, whether in the negative or positive direction. All right, so here's your important points. I have to create a slope field. You just plug in your x and y point into your differential equation and figure out what the slope of that tangent line would be. All right, just remember how slope is related to the steepness of the line. And you just draw a tiny little line at each point, and when you put it all together, you get your slope field. So again, let's just quickly go back to this one. I just see kind of what it looks like for a computer generated one. You see all these little tiny lines, and you can almost kind of visualize following these lines to create your differential equation.